All right. So today I want to continue to work through lecture set number 7 and get as much of lecture set 7 done as possible. Just as a quick reminder, assignment number 3 was due on Tuesday. So the lab quiz number 3, I believe, would be due tonight. And assignment number 4 has been posted, and that is due after the reading week at some point. It might be, probably check that. Okay, so assignment 4 is due November 16th. So that would be the Tuesday after the reading week. And lab quiz 4 is due November 18th, which is the Thursday after the reading week. All right. Yeah, reading week is sweet. Okay, so we're gonna continue to, and then of course the term tests are next week. I sent out an email with some initial details about the tests. There's also a there's also a video on how to access the test if you don't get the link right away. Sometimes what happens is the links will get sent out, like the CrowdMark link to the midterm will get sent out, say 10 minutes before the test opens, and 80% of students will get the link and they'll click it and they'll be fine. And then the other 20%, they might not get it right away. And they typically get a little bit panicked, which is understandable. So I attached a video to the email I sent out about the midterm. And if you watch that video, it basically just shows you another way that you can get access to the test. So this will always work. I've never had any problem with this approach. It's just a little more complicated compared to just clicking a link in your inbox. But if you follow the instructions in that video, that'll 100% give you access to the test right at the start time, so you can get going on it and work through it. But as I had mentioned in the previous email, I'll send more details about the midterm in terms of the exact number of questions and the exact number of marks once I have it finalized. And I will also send another reminder email via Blackboard, and I will send another reminder email individually to you that says which section you're in and which day you write on, in case you aren't fully sure. But as was pointed out last class, like, you can check your section number in My Student System, and then the test time just corresponds to the day that you actually have lecture, essentially. So I believe for ASO3 students, yeah, so for ASO3 students, that would be the Tuesday that you're writing, and for ASO1 students, that would be the Thursday that you're writing. So it corresponds to when you are supposed to be in lecture. Okay, so with that being said, I want to get back into lecture set number 7. What we did at the end of, well, in the last 20 minutes or so of Tuesday's class is work through the first few examples from lecture set 7, which were basically just an introduction to what a confidence interval is and how a confidence interval is interpreted. And what we're going to learn how to do today is actually compute confidence intervals from scratch. So basically, here's your data set. You have little n number of observations in the data set. So, maybe you have 10 observations or you have 20 observations, whatever. Find the some % confidence interval for this data set. That's our goal. And we're going to look at 2 different ways to do this. And the way that we do it is based off of the presence or absence of the population standard deviation. So we basically have a criteria that we need to check for, and that criteria determines how we compute the confidence interval. In terms of interpretation, it's going to be exactly the same as what we looked at last class. So for every confidence interval, we basically have a stock conclusion that we can write, which says we are some % confident that the population mean is between the lower bound and the upper bound. And all we're going to do throughout our time working with confidence intervals is tweak that general statement to suit the exact problem that we are working on. And I'll show you lots of examples of this as we work through the lecture set. Okay, so I had mentioned that constructing the interval is the goal of today's class. And there's basically one major criteria that we need to check for in order to determine how we build the interval. The construction of the interval in terms of formula is actually exactly the same. So the way that we work the formula is not going to change between the two approaches. The only thing that changes is whether or not we use the standard normal table or we use what is called the student's t-table, which I'll introduce in a little bit. So the criteria is the presence or absence of the population standard deviation, which is sigma. So if sigma is known, we're going to use the standard normal table. And if sigma is unknown, we're going to use the student's t-table. To construct a confidence interval about the population mean, we use the parameters of the sampling distribution of the sample mean. So already the material that we learned in lecture set number 6 about central limit theorem and the sampling distribution of the sample mean is coming back into play. So we're actually just extending our abilities, or maybe what I should say is we're building another set of techniques on these same formula or on these same properties. So you should recall that the sampling distribution of the sample mean has mean mu and standard deviation sigma over the square root of n. Okay. When sigma is known, the formula for our confidence interval is x bar plus or minus a z-score. Okay. So notice here that we have our z-score notation. Okay, so this is telling us that we are going to be using a z-score that has alpha over 2 of the area to its right. So this is building on our lecture set 5 skills where we were finding area underneath, or where we were using area underneath the curve to find a z-score. So we're basically always looking up different percentiles of the standard normal distribution multiplied by sigma over the square root of n. Okay, so this whole quantity here, this is our margin of error. So you might recall from last lecture, I'll just very quickly go back and show you that the general confidence interval is a point estimate plus or minus some margin of error, okay? So in the case that sigma is known, our point estimate is x bar. Okay. And our margin of error is z subscript alpha over 2 multiplied by sigma over the square root of n. So our confidence interval basically requires us to plug in these 4 numbers, the mean, the sample mean, sorry, the z-score, the population standard deviation, and the sample size. And then using those 4 numbers, we find our lower bound and our upper bound. Okay. All right, now when we are building this interval, because we are using a z-score, we also require that x bar is approximately normally distributed, which means that we either have to sample from a normal population or we have to collect enough information that the central limit theorem would take over. So the interval, this interval is only valid if we have evidence that our variable is normally distributed. Otherwise, we would not use this approach. Okay, so in general, when we want to construct a confidence interval about mu, we start by identifying alpha. Alpha is very easy to calculate. It's simply 1 minus the percent confidence level. Then we find the z-score based off of alpha. Then we compute the margin of error and find the lower and upper bound of our confidence interval, and then we interpret the interval. So those are the 3 steps in confidence interval construction: find the z-score, compute the interval, interpret the interval. When we use this interval, there are 3 assumptions that we need to check. 1, the sample was collected using simple random sampling. Okay, so we have an SRS. 2, X bar is approximately normal. So this can be done by checking if, this can be done by using the 2 criteria from assignment 3. So if we sample from a normal distribution, X bar will be normal, so that checks it off. Or if we collect more than 30 observations, X bar will be normal, so that checks it off. And then in order to use the Z-score, we also have to have sigma known. Okay, so if sigma is unknown, the Z-score will change to a t-value, and we'll talk about that in a little bit. Okay, so here's an example of how a confidence interval would be constructed. Suppose the data on slide 4 is a simple random sample. Okay, so we have simple random sample from a normally distributed population. Construct a 95% CI for mu. Okay, so this data set shown here has 10 observations. This is the same data set that was shown on slide 4. The sample mean for the 10 observations is 108.3. And suppose that we are told that sigma is 20. So this would have to be given to us because we wouldn't be able to calculate population standard deviation. All right, so we can do, before we go into the construction steps, we would make a quick list and check to see if our assumptions are intact. Okay, so this would be the starting point before we actually build the interval. So the first assumption is that we collected a simple random sample. From the description of the problem, you can see that it tells us that we have an SRS, so a simple random sample. So this assumption is good. The second assumption is that X bar is approximately normally distributed. We are told that we collected data from a normally distributed population. Therefore, X bar is going to be normal because we are sampling from a normal population. So this assumption is good. And then the last thing is that we require sigma to be known. Sigma is given to us, so this assumption is good. So that means that we can use the confidence interval and we can use the Z-score to build the confidence interval. Okay, the first thing that we do is work out Z subscript alpha over 2. So alpha is going to be 1 minus the percent confidence level, or 1 minus the confidence level as a decimal place. So here I have alpha 0.05. That's because 0.05 is equal to 1 minus 0.95. Okay, so we are told to construct a 95% CI. So alpha is just 1 minus 0.95. So that percent as a decimal place. The next thing that we need to do is find the Z-score. So we have Z subscript 0.05 over 2, which is Z subscript 0.025, which is 1.96. Okay, so here, this is just our, this is us just revisiting, working with the standard normal table. So we have a standard normal curve. We have Z 0.025 here, such that this area here is a size of 0.025. And all we need to do is figure out what Z-score makes this area a size of 0.025. Okay, so here's, if we have 0.025 to the right of the Z-score, that means that we have 0.975 to the left of the Z-score. So if we go to our normal table and we look up 0.975, okay, that corresponds to a Z-score of 1.96. right? So this is, again, just finding percentiles underneath the standard normal curve, which is a technique we learned in lecture set 5. Okay, so that's where the 1.96 comes from. Okay, so then in step 2, we have our formula for the interval is x bar plus or minus z alpha over 2 times sigma over the square root of n. So that's going to be 108.3 plus or minus 1.96 times 20 over the square root of 10. You can see all we're doing here is plugging into our formula. When we solve for the margin of error, we end up with 108.3 plus or minus 12.396. We add and subtract that value, and that gives us the lower bound of 95.904 and the upper bound of 120.696. And then we can conclude by saying we are 95% confident that mu is between 95.904 and 120.696. Okay, so that's in the simplest situation, this would be an example of confidence interval construction. The only thing that gets trickier really is in the context of word problems is identifying the information that you have, but the steps will always be as illustrated on this slide. Any questions? Okay. Okay, so for the same data set, construct an 85% confidence interval for mu. So we're repeating exactly what we did in the previous exercise, but we're changing the percent confidence level now. So the assumptions here are going to be exactly the same, and we're going to have the same result because it's the same data. So the first thing we do is check our assumptions. So we have SRS, we have normality of X bar, and we have sigma known. Okay, so each of these is intact because we are told that we have a simple random sample, that we have normality, and that we have sigma. Okay, so the same logic as on the previous example, because it's the same data set. Okay, step 1, we're going to find Z alpha over 2. Okay, so alpha is 1 minus 0.85, which is 0.15. Z alpha over 2 is Z 0.15 over 2, which is Z 0.075. Okay, so we have 0.075 of the area to the right of the Z score of interest. So because the confidence interval adds and subtracts the Z score, we can actually just go to the negative table and look up 0.075 directly. Okay, so that's going to be closest to this value here. So that gives us negative 1.44. So that means that our value here is just going to be 1.44. But because of the symmetry of the curve, we're actually able to kind of, take this sneaky approach and just look up the negative and then make it a positive. But even if we left it as a negative, you would get the exact same answer because you're adding and subtracting the value. Yeah, but again, you don't need to include the negative because you're adding and subtracting the value. If you want to leave it as a negative, you can, but again, you'll get the exact same answer. As long as you put the lower number first, it won't make a difference. Okay, so then on step 2, we're going to sub in and compute the interval. So we have x bar plus or minus z alpha over 2 multiplied by sigma over the square root of n. So this is going to be 108.3 plus or minus z 0.075 multiplied by 20 over the square root of 10, which is 108.3 plus or minus 1.44 multiplied by 20 over the square root of 10. Okay, and this is going to give us a number that I, of course, didn't decide to calculate. So that's going to be 108.3 plus or minus 9.10736. So then we're going to have 108.3 minus 9.10736 to 108.3 plus 9.10736. That's going to give us 99.193 to 117.407. All right, and then we conclude by saying we are 85% confident that mu is between 99.193 and 117.407. Any questions? Okay, so some notes on the confidence intervals. We have now seen 2 examples for the same data set where we changed the confidence level. When we change the confidence level, but we hold all of the other values constant, so when we have the same sample size, we have the same standard deviation, all we're doing is changing the percent confidence. This is going to result in a, well, I guess a less accurate. Oh, hold on a second. Yeah, this is okay. That's sorry, I got thrown off because I have this thing is There we go. Okay, so when we increase the confidence level, we're going to have a less accurate interval. So we sacrifice basically how wide the interval is, so how close the interval is to the mean, for increased confidence. So what I mean is, for example, we just considered an 85% interval. Oh man, I am on today. So consider these 3 bars that look like this. So each of these is going to be a confidence interval. So this is our 85% CI. This is our 90% CI. and this is our 95% CI. You'll notice that as we increase the confidence level, the interval is getting wider. So that's what I mean by the interval being less accurate. When we want more confidence, so I want to move up to 95% confidence from 90, I sacrificed how accurate the interval is, which just means that I have a wider interval. So it means that there's a larger range in which mu can fall in between. So we're not as sure where mu might be at the higher level of confidence, but we are more confident it sits in that range. So there's this trade-off between the two approaches, right? So for each of these intervals, we actually have the bounds. So this is going to be 99.193. This is going to be 117.407. This is going to be 97.90. This is going to be 118.7. This is going to be 95.90. And this is going to be 120.70. And yeah, and that suffices to show the example. So basically the point is, for the same data set, you might say, well, why don't we always just max out the confidence level? Like, let's just use 99% confidence every single time and take the highest percentage. You can do that and increase your level of confidence in where mu is going to lie, but you do it at the sacrifice of accuracy, which means that when you take the highest percent confidence level, you have a larger range in which mu could belong. So you're actually not as sure what value mu might take on, but you're more confident it sits within that higher range. So there's a trade-off between percent confidence level and accuracy. Okay, another example. A sample of 678 females believes that on average, 3.22 children is the ideal number for any family. Find and interpret a 90% interval for mu if sigma equals 2. Is this interval valid? Why or why not? What is the length of the interval? All right, so we want to compute a 90% CI for the population mean based off of this information. Okay, so let's write down what we have. Our sample size is 678. Our sample mean is 3.22. Our population standard deviation is equal to 2. Okay, the assumptions are that we collected an SRS, that X bar can be considered approximately normal, and that sigma is known. All right, so we're not actually, it just says a sample of 678 females believes that this is true. It doesn't say a simple random sample. I say, let's just assume that this is okay and that the sample was collected reasonably. So assume it is a SRS. The second assumption is normality. So we can say, yes, X bar is approximately normal by the central limit theorem, since n is greater than 30. So we have 678 observations. The central limit theorem says if n is greater than 30, X bar will be approximately normal. So 678 is clearly larger than 30. So then we can say X bar is approximately normal by the CLT. Number 3 is that sigma is known. This is good because we're told sigma is equal to 2. All right. So now we can start to fill in the interval. Okay, so we have alpha equals 1 minus 0.90, which is equal to 0.10. So then we have z subscript alpha over 2 is z subscript 0.1 over 2, which is z 0.05. Okay. So now we're looking up the z-score that has 0.05 of the area to its right. Okay, so again, we can use our little trick here because of the symmetry of the curve. Okay, so we're looking for 0.05 within the table. We can see that 0.05 is directly in between 0.495 and 0.0505. So it's the average of these two values. Okay, so this is that special case where we can average the two z-scores. So we're going to take the average of negative 1.64 and negative 1.65. Okay. So this is going to be 1.64 plus 1.65 over 2, which is 1.645. Okay, so now on step 2, we're going to have x bar plus or minus z 0.05 multiplied by sigma over the square root of n. So this is going to be 3.22 plus or minus 1.645 multiplied by 2 over the square root of 678. That's going to be 3.22 plus or minus 0.12635. Then we're going to add and subtract this. So we'll have 3.22 minus 0.12635 to 3.22 plus 0.12635. And that gives us 3.093, 094 to 3.346. Okay. Now we have to interpret the interval. So in this case, the population mean that we are trying to estimate is the mean number of ideal children that female, or the is the average number of children that females consider to be ideal for the family. So we want to include that description in the interpretation. So we can write something like this. We are 95% confident that this population of females believes that between 3.094 and 3.346 children is the ideal number for any family on average. Yeah, 90, thank you. Okay, so what we have found here is that based off the sample, the population of females that we are studying believes that the ideal family will have between 3.094 and 3.346 children on average. So, this is implying that this population considers, just about 3 children to be the ideal number, but it's actually giving us evidence that they would prefer to have more than 3 children, but you can see the bounds here don't include 4. So I would think the implication here would be basically like at least 3 is the ideal number. Okay, part B asks, is the interval valid? Why or why not? So when we're talking about validity, we're basically just saying, does the interval check off the assumptions of the test? So since all assumptions are met, the interval is valid. Okay, so validity is just saying, do you have evidence that the assumptions have all been checked off? Okay, in part C, we're asked for the length of the interval. Okay, so length of a confidence interval is just the upper bound minus the lower bound. So length is equal to upper bound minus lower bound, which is 3.346 minus 3.094, which is 0.253. Okay. Any questions? Okay, so we have learned how to construct a confidence interval when sigma is known, and then the other two assumptions are checked off. But those first two assumptions, simple random sample and normality of X bar, those are always going to be there. The differentiator between the two types of intervals that we're going to learn how to compute are whether or not sigma is present. So when sigma is known, we use a z-score, and we have now seen 3 examples of how that interval would be constructed given we have the z-score. Okay. The length of the interval is always the upper minus the lower limit or the lower bound. Okay, so it's just the higher values minus the lower value. The center of every confidence interval is always the sample mean. So if you were to average the two bounds, you would get the sample mean because the interval is X bar plus or minus the margin of error. The margin of error is equal to the z-score multiplied by sigma over the square root of n. So that means that we can make interpretations about the size or the length of the interval based off of changing one of those values and holding the others constant. So for example, if for the same data set, I have consistent sample size and consistent z-score, the larger the population standard deviation, the longer the interval is going to be. Similarly, if I have the same sample size and the same population standard deviation, the higher the confidence level, the longer the interval is going to be. Okay, so we can understand how the interval is going to respond to changing the margin of error quantities, given that we hold the other values fixed. Okay, the next thing that we need to learn how to do is compute a confidence interval when sigma is unknown. All right. This is actually a very straightforward process. Basically, all we're going to do is replace sigma with little s, where little s is the sample standard deviation, and we learned how to compute this back in lecture set number 2. So the formula that we are using, that confidence interval formula, is actually exactly the same in the situation where sigma is unknown. The only difference is that the z-score becomes a t-value and sigma becomes little s. So now we're going to have X bar plus or minus t alpha over 2 n minus 1, I'll get to that in a second, multiplied by s over the square root of n. Right. Very briefly, when you take the z-score equation for the mean, so that's shown in equation 3, and you replace sigma with little s, the z becomes a t. So basically all we're saying here is when you standardize x bar using sigma over the square root of n, you get a z-score. When you studentize x bar by dividing by little s over the square root of n, you get what's called a student's t random variable. So these are random variables that belong to different distributions. So when we have sigma and we standardize x bar, we get a z-score. When we have little s and we studentize x bar, we get a t value. So we are going to learn how to work with student t random variables in what remains this lecture, and we'll see more examples of that in lecture set 8. The student t distribution, like the standard normal distribution, has a table that is associated with it. So basically working with the distribution just amounts to learning how to use a different table. And in the case of confidence intervals, this table is actually very, very easy to navigate. Some quick properties. The student t random variable is a symmetric bell curve distribution that's centered at 0. So it has the same shape as a standard normal. However, a student t distribution has a parameter called the degrees of freedom. The degrees of freedom, which is simply the sample size minus 1, controls the shape of this bell curve. So you might recall that with the standard normal distribution, when you increased the variance, the tails came out and the peak went down. And when you decreased the variance, the tails went in and the peak went up. The degree of freedom does the same thing to the student t distribution. So when you increase degrees of freedom, the peak comes up and the tails go in. And when you decrease degrees of freedom, the peak goes down and the tails go out. The reason why this is important is because the degree of freedom specifies how wide the tails are, but these tails are actually quite a bit wider than the standard normal distribution. So the idea is the student's t distribution is more robust to outlying points. So it can stretch itself further compared to the standard normal. All right, so here's an example of what I'm talking about. This red curve is the standard normal curve. Okay. And this black curve, this is students' t curve for new, well, let's just say for some small new, for a small new, for example, new equals 10, right? I don't know what exactly the degrees of freedom are, but it's definitely a small number. So something like df is equal to 10. Okay, so you can see like what's happening here is compared to the standard normal curve. When you have a student t curve with degree of freedom equal to 10, you have a lower peak and you have higher tails. Okay. So as new increases, peak of students t goes up, tails go in. Okay, so this is what I mean. As we increase new, we have a peak that comes up to meet the standard normal curve, and we have tails that come in to meet the standard normal curve. So basically, for a very high sample size, the student's t-curve is going to look exactly the same as the standard normal curve. And then if nu decreases, peak goes down and tails go up. Okay, so when we decrease nu, we simply have the opposite effect. Okay, so all of this is just a little bit of food for thought so that you can understand how the student t-curve relates to the standard normal curve. In terms of our immediate goals, we need to learn how to work with the student's t-table, which, as I mentioned, for confidence intervals is actually quite straightforward. And we need to learn how to build the confidence interval for a student t random variable, or based off of a student t random variable. But this process is identical to what we have already seen. So it's not going to take a lot of extra work to see how you fill the formula in. Okay, so the main difference is going to be the formula now uses a t-value instead of a z-score. So we need to learn how to find t-values using the student t-table. Okay, so to illustrate how this is going to work, we're going to look at 4 examples of finding t-values. In each of these cases, the t-value is going to appear the same way that it would in a confidence interval style problem. So the first question here says find t subscript 0.025, 15. Okay, so this means that we have 0.025 of the area to the right of the t-value, and we have 15 degrees of freedom. Okay, so nu is equal to 15. Okay, so basically we can set this problem up in the same way that we would do a normal problem, because the student t curve is a symmetric curve about 0. So we can make a little sketch here. There's 0. Here's t subscript 0.025, comma 15. Okay, so this red shaded part here, that's a size of 0.025. All right, so to find the t-value, we go to the student t-table. So the student's t-table is shown here. There are, again, 2 pages to this table. So this is page 1, and here's page 2. The only difference is that page 2 starts at DF50, page 1 starts at DF1. So it's kind of like you would read it vertically, like they would stack on top of each other and you would work yourself all the way down. You'll notice that as you scroll through the bottom of the table, you'll see that the values inside the table, which are the t-values, are getting smaller and smaller. If you continue to scroll all the way to the end of the second page, you'll notice that these values converge to z-scores. So the point is, for high degree of freedom, you have t-values that match the z-scores. So the t-curve conforms to the shape of the standard normal curve. All right, we have t subscript 0.025, comma 15. So the top of the t-table gives us our subscripted values. So that's area to the right. Okay, so we're going to take t 0.025, which is the value that we have. We're going to match that to the degree of freedom, which is 15. And that means that our t-value is 2.131. Okay, so hopefully you'll notice here that looking up the t-value is very straightforward. It's simply a matching of degree of freedom to the area of the right, to the tail area to the right, and then you just come into the table to find the value. So all of the values inside the t-table are actually axis values in this case. They're not probabilities. So in that sense, it's kind of the opposite of the normal table, but it makes looking up t-values very easy. Okay, so now that means that our value here is 2.131, and that's the solution to the problem. Any questions? Yeah, they're not. T-values are axis values. So they run along the bottom of the curve. T-value is like a z-score. It runs along the bottom. Okay, exercise 2, find t 0.05, 12. Okay, so same style of problem. Okay, so here's my t curve. Here's 0. So now I have t 0.05, 12. Okay. So all I need to do here is match t 0.05 to 12. So I go back to my normal my t table. Here's t 0.05, here's 12, here's my t value. Right. Exercise 3 says, what student's t random variable has 0.05 of the area under the curve to its right when n is equal to 12? Okay, so same problem. So we're here, we have t 0.05. So we're told that this is a size 0.05. Okay, and then we're also told that n is equal to 12. So we know that the degree of freedom is n minus 1. So that's 12 minus 1, which is 11. So this is a t value at 0.05 and 11. Okay, so we go back to our t table. We have 0.05, we have 11, and that gives us 1.796. Okay, exercise number 4. What student's t random variable has 0.9 of the area under the curve to its left when the degree of freedom is equal to 12? Okay, so in this case, we have a t value that's here, and we're told that to the left of it, we have 0.9. So that means that this red shaded part here is a size of 0.1. So that means that our t-value is going to be the t-value on 0.1 and 12, because the question also says that we have 12 degrees of freedom. So now we go back to our student t table. We're going to match 0.1 to 12, and that gives us 1.356. So that's 4 exercises of how to find a t-value. And as I mentioned, it's basically just a matching of area to the right to degree of freedom, and then you just come into the table to find the value. And again, those are not probabilities, these are axis values. Any questions? Okay, so now that we know how to find the t-value, we're going to go through a few examples of building confidence intervals when sigma is unknown. This again is going to be the exact same process that we had started at the beginning of lecture today. So the formula is effectively identical. The only difference is sigma is replaced with little s, and the z-score is now replaced with the t-value. So we're going to be taking the exact same approach that we studied in those 3 confidence interval examples that we used in lecture today. But now that sigma known assumption is not going to be met. So we have to use little s instead of sigma. And as a result, the z-score changes to a t-value. Right? The assumptions of this interval are exactly the same as the assumptions of the standard normal interval. The only difference, again, is that sigma is not known. Okay, so the general rule is sigma known use z alpha over 2 if sigma is not known, use t alpha over 2 n minus 1. So this is the key thing that we need to look out for when we're working through these kind of problems. Do we have sigma or do we not have sigma? If we have sigma, z-score. If we do not, t-value. Otherwise, we still have to have a simple random sample, and we still have to have evidence that X bar is normal. That never changes. All right. Compute a 99% confidence interval for mu using the following simple random sample taken from a normal population. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. So we have little n is equal to 10. We do not have any population information, right? So we just have our sample and we have some summary statistics shown below. So we have the sum of xi is equal to 15.2, and we have the sum of the xi squared is 426.7904. Okay, so the assumptions are one, that we have an SRS. You can see from the problem description that this is true. So we're told the following SRS is taken from a normally distributed population. So the first assumption is fine. The second assumption is normality. Okay, we are told that this is taken from a normally distributed population. So this assumption is also fine. Okay, now the way that I like to do it is I still like to write down if sigma is known. And in this case, you can see that this isn't true, but that's okay. It just means that we have to use the t value. So not knowing sigma does not stop the process. It just says, okay, we don't have this. We're going to use a t value instead because x bar is still normal and we still have an SRS. Okay, so on step 1, we're going to have alpha equals 1 minus 0.99, which is 0.01. So that means that we're going to have a t value on alpha over 2 n minus 1. So this is going to be a t on 0.01 over 2 and 10 minus 1. This is a t on 0.005 and 9. Okay, so we know how to find this value. We go to the t table. We're going to match 0.005 to 9. That gives us 3.250. Okay, so then on step 2, we have x bar plus or minus t 0.005 comma 9 multiplied by s over the square root of n. Okay, so we have the t value, we have little n, we don't have x bar, and we don't have s. So x bar is going to be, or the formula for x bar is the sum from I equals 1 to n of xi divided by n. So we're actually given this sum in equation 7. So this is going to be 15.12 divided by 10, which is 1.512. Right? So now we have x bar. Okay, now we also need to work out little s. So we know that little s can be computed using the defining formula or the computing formula. We are given the sum of the xi squared. So to work out little s, we're going to use the computing formula. So we have the sum from I equals 1 to n of xi squared minus the sum from I equals 1 to n of xi all squared divided by n all over n minus 1. So that means that little s is going to be the square root of 426.7904. Okay, 426.7904 minus 15.12 squared divided by 10. Remember that this is all one calculation, divided by 10 minus 1. This should work out to be the square root of 44.881, which is 6.69933. Okay. Okay, so now we can plug in. So we have X bar plus or minus T 0.05 comma 9 multiplied by S over the square root of N. So that's going to be 1.512 plus or minus 3.250 multiplied by 6.69933 divided by the square root of 10. So that's going to be 1.512 minus, or actually let's do it like this, plus or minus 6.881571. 5171. Okay, so then we're going to add and subtract this value. So we have 1.512 minus 6.8815171 to 1.512 plus 6.885171, which is negative 5.373 to 8.397. Okay, and then we can just say we are 99% confident that mu is between negative 5.373 and 8.397. All right. Any questions? Yeah, exactly. The conclusion is exactly the same. The only difference is how we calculate them. Okay, one more example. From an SRS, estimates of the theoretical spring constant for 6 type 1 springs gave X bar 2.03 and S equal to 0.068. Construct a 95% CI for mu. All right, so pretty straightforward problem. We just want to find a confidence interval for mu. We're given a set of summary statistics and we have a normal probability plot. Okay, so the assumptions are 1, SRS. This is true because we're told it's an SRS. 2, normality. Okay, so here we can say since the normal probability plot shows a linear relationship, we have evidence that the 6 type 1 springs come from approximately normally distributed population. Therefore, X bar has a normally distributed sampling distribution. Okay. Kind of a long explanation, but it's the same general idea. We need to show that X bar is normal. In this case, we have the QQ plot, or the normal probability plot. The normal probability plot is showing us a linear relationship. Therefore, the variable of interest, which is the theoretical spring constant, must be normal or approximately normal. Since this is approximately normal, that would imply that X bar is approximately normal as well. So that checks off the second assumption. And then in the third case, here we would just say, no, we don't have that. But that's okay because we have S, so we can just use the T interval. Okay, I'm gonna scroll over. Okay, so on step 1, we have alpha is equal to 1 minus 0.95, which is 0.05. So then we have T alpha over 2 n minus 1 is T 0.025 comma 5. So now we're going to go to our student T table. Okay, so we're going to match 0.05 to 5. Oh, sorry, 0.025 to 5. And that gives us our T value of 2.571. Okay, so then on step 2, we have X bar plus or minus T 0.025 comma 5 multiplied by S over the square root of n. So that's going to be 2.03 plus or minus 2.571 multiplied by 0.068 over the square root of 6. So that's going to be 2.03 plus or minus 0.071373. So that's going to give us 2.03 minus 0.071373 to 2.03 plus 0.071373, which is 1.959 to 2.101. Okay, and then we just say we are 95% confident that the population mean TSC of type 1 springs is between 1.959 and 2.101. Nice. Noise. Noise, noise, noise. Okay, any questions and or comments and or concerns? General inquiries. Okay, so that brings us to the end of lecture set 7, which is great. So lecture set 7 was devoted to finding confidence intervals for the single sample. So confidence interval for one population mean when sigma is known or unknown. Okay, lecture set number 8 is going to demonstrate how to perform a hypothesis test for one population mean when sigma is known and unknown. Very similar idea, just a different procedure so that we can ask a question about the population mean. I'm going to record a video for lecture set 8, and I'm going to post this online before Tuesday, such that the class that is writing the test on Thursday can watch it on Tuesday, and the class that's writing the test on Tuesday can watch it on Thursday. At the conclusion of that video, you will have everything you need to complete the next assignment. When we return from the break, I will do 2 examples from lecture set number 8 to just refresh what we are working on, and then we'll move on to lecture set number 9. As a reminder, the midterms are next week. I'm going to send out a couple more reminders about this, more details once I finalize the test. And I guess this is the last time I'll talk to you guys via like live lecture video until after the break. So good luck on the midterm and then enjoy your reading week. But again, there will be one more asynchronous lecture where I pretend to talk to you guys even though you're not here. I'll post that before Tuesday so that you have it for the week. Yeah, that's what the outline has it at. Yep. Okay, so yeah, I guess I'll talk to you guys in a live setting in a couple of weeks then. And have a good weekend and enjoy your reading weeks.